Do you know why quantum chromodynamics is so hard? You have probably studied about the strong nuclear force in your high school, which tells that this is the force which is responsible for binding the nucleons together in the nucleus, which is correct. But it is not that easy, my friend. You have probably studied that this nuclear force, the strong nuclear force, is charge independent, that it does not matter that what type of nucleons that you have. It could be positive, it could be chargeless neutron, and still they will interact to each other and will make a bond. But the more advanced explanation that you will get at the very beginning of the quantum field theory, the nuclear physics, I should say, that it is the Yukawa's theory, where we think of this interaction as an exchange force. That is a particle, a virtual particle is emitted in this process, and it is called a pion exchange. Even I have made a video on my page about exchange force. You can check it out. From there you will easily understand how this interaction actually works. I gave you an example of electron scattering also, so you will get it. But my friend, those electron repulsion or attraction example that I gave you, they were quantum electrodynamics. They were not the quantum chromodynamics. I would say that quantum electrodynamics is for beginners, but the quantum chromodynamics is the actual picture where you really require an advanced depth understanding. Why? Because if you have watched that video, then you saw that in quantum electrodynamics we see these interactions as exchange of virtual particles, which mediates the force which carries the momentum. And for instance, if you have two electrons, then in this interaction the repulsion can be viewed as an emission or exchange of a virtual photon. And if you emit two photons in this process, those photons will not interact with each other. But when you talk about the quantum chromodynamics, here we have 36 types of quarks. We have in general six quark flavors, and anti-6 quark flavors, and they possess three colors: red, green, blue, and their anti-colors obviously. So you get a total 36 types of quarks, and they interact through exchange of virtual particle, which is known as gluons. And gluons are not only one type of my friend. There are 8 types of gluons. That is 8 types of colors of gluons, and these gluons actually interact with each other. They are non-Abelian gauge group. So for instance, in an interaction you meet a gluon and in another particles interacting in the nucleus, and it emits another gluon. So those gluons will also make interrelation, make an interaction between each other, and this makes this quantum chromodynamics way more harder than quantum electrodynamics, because in quantum electrodynamics we don't see that mediators actually interact with each other, because in quantum electrodynamics this symmetry group is denoted as U1, which is an Abelian gauge group. That is, they don't interact with each other. And so I could explain you with this using the commutation relation, which actually requires the foundation of quantum mechanics, so I will not explain here.